Today we have a great speaker, TS Dr. Muhammad Firdaus Malek. This topic today is synthesization of zinc oxide nanowires and their potential applications. Before we start, let me introduce speaker first. Okay, Dr. Muhammad Firdaus Malek is a senior lecturer from Faculty of Applied Science, UiTM. Currently, he is an active fellow researcher from Nanoscience Lab, Functional Materials and Nanotechnology Center, Institute of Science. His current postgraduate student including ongoing 2 PhD and 9 master students. Dr. Firdaus also as a one of editorial board for Nanoscience and Nanotechnology Asia Journal. Very interesting. He was awarded as a Royal Chancellor's Excellent Doctoral Award 2017, Excellent Researcher Award 2017, and Graduate On Time Certificate 2017. Congratulations, Dr. Firdaus, for your achievement. Okay, ladies and gentlemen, if you have any question during his presentation, just write them to the chat room. Okay, without further ado, I would like to welcome the speaker to deliver his presentation. Dr. Firdaus, the slot is yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Dr. Muhammad Firdaus bin Malek, and I'm from Nanoscience Lab, Center for Functional Materials and Nanotechnology, Institute of Science. And today I will present on the topics of synthesization of zinc oxide nanowires and their potential application. So today will be a general introduction. I consider some of you are not in this field. So we go to the outline. First, I will introduce on the zinc oxide itself, and then what is nanowires, and then how to synthesize the zinc oxide nanowires, and also the application of the zinc oxide nanowire. Okay, so what is zinc oxide? So zinc oxide is an inorganic compound with the formula ZnO. It usually exists in white powder, which is insoluble in water. It is widely used as an additive in numerous materials and products, including your food supplements, your car tires, usually used during the vulcanization process, and as an accelerator and activator to improve elasticity, tensile strength, hardness, and also for weather resistance. And it also be used in plastics, ceramics, glass, cement, lubricant, tin, and mostly they are widely used in cosmetics. Okay, point on cosmetic, I just want to share with you. Actually, the zinc oxide, the oxide material, especially zinc oxide and TiO2 are widely being used in cosmetic. So for your information, between 2003 until 2014, the scientific committees of the European Commission, they released several opinions on the use of zinc oxide on cosmetic, which can lead to lung toxicity and inflammation. Some of them also claim that some also have made tests, and they suggest that the use of zinc oxide could also lead to cancer. So in view of this, the European cosmetic regulation lists down to not using zinc oxide and titanium dioxide nanoparticle in application that would lead to any significant inhalation exposure, such as powders and sprayable based products. Okay, this is for cosmetic. So it is suggested that both forms, which is the powders and sprayable products, they suggest to and authorize both of this product at a maximum concentration of 25%. So you check, especially women, those who use the cosmetic, or especially in our country, there are
So saya boleh remove this one Cisco.
Okay. 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 So because we have too many products in our market right now, especially for Mohd, so you have to check whether the use of these outside materials in the products.
Yeah.
Okay. And then zinc oxide also is a wide bandgap material, which is have several characteristics that make them useful compared to narrower bandgap material. So the higher energy gap give devices the ability to operate at higher temperature, as bandgap typically shrink with increasing temperature, which can be problematic when using conventional semiconductor. So this zinc oxide also transparent to visible. Okay, now zinc oxide nanostructure. Zinc oxide is the material which is easily to form with various of nanostructures, such as nanowires, nanobelts, nanocombs, nanospring, and etc. So uh, it can be synthesized by easily just playing with the parameters such as the temperature, the deposition temperature, the doping process, the annealing process, and so on. So the process to synthesize these nanostructures are controllable by this kind of parameter. For those who are not familiar with the nano size material, so here you can see the range between 10 power of negative 2 meter to 10 power of negative 10. So here is the range of the technology that we are using in our research, okay, which is smaller, 10,000 smaller of our hair diameter. Okay, so we go for specifically for nanowires. So what is nanowires? So nanowires is one form of nanostructures, which I already mentioned to you before, with the diameter of the order of a nanometer, which is 10 of power negative 9 meters. It can also be defined as the ratio of the length with the width being greater than 1000. Okay, and alternatively, wire can be defined as structure that have a thickness or diameter constraint to 10 of nanometers or less. Okay, you can see as you can see from the figure here. So this is a shape of the nanowires. So here the outside formation. Okay, this one is not nanowires. Okay, okay. Let's see what CM Lieber say about this structure. The nano, yes, they represent the smallest dimension for efficient transport of electron and excitons, and thus will be used as interconnects and critical devices in nanoelectronics and optoelectronics. So as you can see here, the development of the transistor, okay, from 1917 to until now, but it was increased until now to 2020. For now, what I have known, the IBM, they already achieved until 256. They are one of the first company that achieved the value of 256 at March 2020. So this is just their projection. So one dimensional nanostructure represent the smallest dimension structure can efficiently transport electrical carrier, which is the electron and hole, and also can act as both nanoscale devices and wiring to link components into extremely small circuit. Okay, especially for our electronic components nowadays, which is more than compared to years ago. So this is one of the technology that contribute to that. So why nanowires? So nanowires, the first one, it is increase in terms of surface area, and then the diameter is dependent bandgap, increase surface scattering for electron, okay, and then it can be control. It is a control synthesis. So just I mentioned to you before, where we can control the length and the diameter that we want through the parameter like the concentration, the time deposition, and etc. And also for quantum confinement, which is contribute to unique magnetic electronic properties. So this quantum confinement effect also will describe the electronics in terms of energy level, potential well valence band, and also the conduction band. So the conduction confinement effect can be observed when the size of the particle is too small, okay, which refer to the nanowires, comparable of the wavelength of the electron. So we go on the synthesization part. So nanowires can be synthesized into various number of deposition technique. Okay. Wow. This is several numbers of deposition technique that can be applied, such as e-beam lithography. Okay. So this development of one-dimensional structure for long, it is actually hindered difficulties associated with its synthesis and fabrication, such as how to control the dimension, the morphology, chemical, and the composition. So this technique, such as e-beam lithography, focus ion beam, as chemical vapor deposition, evaporation, condensation, laser assisted growth, template-based synthesis, and also solution phase synthesis, which is quite wide use to produce ZnO nanowires. So I will discuss some of these techniques in the following slides. So I will not discuss all, just a few one. Okay. So one of the method to produce zinc oxide nanowires is through vapor liquid solid growth. Okay, so by showing this figure, I think some of you which is familiar, I think chemistry, they are quite familiar with this technique. So vapor phase synthesis technique were being used extensively for the synthesis of nanostructure. So vapor phase technique can be broadly classified as a vapor liquid solid, okay, which is VLS, okay, short form, and vapor solid growth, okay, VS. So VLS technique is utilized mostly for the synthesis of zinc oxide nanowires and other materials as well, including zinc oxide. So in this technique, nanowires are synthesized using gaseous precursor reactants. Since the reactants are in the gas phase, so it is easy to organize and manipulate the nanostructure in order to obtain crystalline and defect-free nanowires. And this technique has been used since around 1960. So it quite long ago. They found how to synthesize this kind of structure. Okay, here they are using a catalyst, okay, substrate, and gas flow to develop the wire into the direction that they want. Okay, so in VS, okay, one. Okay, so here for this I will introduce. Okay, here we are using metal. So metal. Okay, so usually they are using iron or gold as a liquid catalytic nanocluster. Gold particles we use as a catalyst for the growth of nanowire. So this one is based on the previous research or the earliest research, how they find grow the nanowire based material. So in this case, they are using silicon. Okay, so here you can see that gold particle are used as a catalyst for the growth of the silicon nanowires from various sources of vapor, such as silicon tetrachloride, CiCl4, or silane. Okay, so this basic concept of VLS growth was approached for the growth of zinc oxide. So what happened is, initially this gold particle will be deposited on the silicon substrate, okay, which result the evolution of gold silicon droplet specific temperature. Okay, and then the melting point of the gold silicon alloy at eutectic temperature is very low compared with silicon or gold themselves. So the formation of silicon gold droplet on silicon surface from gold particles is possibly only above 362 degrees Celsius, which is more than, is actually 363 degrees Celsius. And then the catalytic effect is responsible for the reduction of silicon at the gold droplet. So the gold silicon droplet absorb vapor phase silicon resultant in a supersaturated state. And then silicon atom precipitate from the supersaturated droplet because the melting point of the silicon is higher, and this result will form the growth of the silicon nanowires. Okay. So here, this one metal, they are using gold. Okay, so this one will lead to the formation of the silicon wires. Okay, so the same approach are used to develop the zinc oxide nanowires on this method, where here silver was used as a catalyst. Okay, you can see it from the figure. So this one is the temp of a single crystal zinc oxide nanowire. So this tip is the silver. So this one is the cross section of the zinc oxide nanowires. Okay. So this is confirmed we can synthesize this zinc oxide nanowires using the same method. Okay, now we go for the method, which is also quite famous. Okay, so we are also using this method in our lab, which is the chemical vapor deposition. So the chemical vapor deposition is an attractive solution for synthesis zinc oxide nanowires at large scale without incorporation of catalyst compared to previous method. They are using catalyst to form the nanowires. So the catalyst-free approach ensures the production of high purity of zinc oxide nanowires compared to the VLS growth approach. So you can see here, the zinc oxide is actually produced on the silicon substrate. Okay, so the silicon, the synthesis was carried out in two sectors of this quartz substrate. So this one is the first furnace. This one is the second furnace. Okay, so we are using the argon and oxygen gas are being used. Okay, and then the precursor of zinc will be placed at the first reactor or the first furnace. So the zinc was evaporated in the first furnace. Okay, it will evaporated in the first furnace while it interact with the oxygen in the second furnace. So the silicon substrate here, okay, so the reactor pressure was kept at a certain level, usually to 4 to 5 torr, and oxygen argon mixture will allow to flow inside the reactor at a constant rate. So the temperature is up to the during the what we call optimization process. So it is usually more than 400 degrees Celsius. Okay, so the deposition time in this case was varied between 10 to 40 minutes. So you can see here that the length of the nanowires is very increased with from 63 micrometer to 181 micrometer. And then finally, the last step that I want to discuss with you is the solution phase method. Okay, solution phase synthesis or method. Okay, this method is generally carried out in a solution. Okay, in this we are using water base. Okay, and whenever it is carried out in an aqueous, it is called hydrothermal growth method. Okay, the alternative name that has been widely being used. But before that, a few layer of zinc oxide nanoparticles seeded on substrate and seeded particle promote nucleation for nanowires growth is need to be considered to be synthesized on top of the substrate before the synthesization of the nanowire. Okay, so as you can see here, so the precursor that are being used here. So we are also introduce the sonication process to enhance the what we call the homogeneity of the solution. And then in this case, we are using the deep coating process. Okay, we are also doing on the spin coating, and then it will go for preheating and annealing temperature for the development of the seeded catalyst layer. Okay, and then for the development of zinc oxide wires, so the same zinc base solution was being used. Also, we are introduce the sonication process to speed up the the homogeneity of solution, and we pour it into a vessel, Scott bottle, and then we put it in a water bath for the evaporation process. And then here is the process to grow the nanowire, and then we go for annealing process for the to make it crystalline structure. So until we get the zinc oxide nanowires. So okay. So this is from our result. Okay, so you can see here we synthesize the zinc oxide nanowires at 2 different times, which is 1 hour, and then this one is for 2 hours. So this one 1 hour is, you can see from the scale on the FSM result, it is less than 1 micron actually, this one. So if you can compare with the scale here, I forgot to measure it directly from the FSM image. So this one is more than 1.5 micron. Okay, so you can see on the difference is when you increase the time, the length of the nanowire is increased. Also on this one is the top morphology. As you can see here, yes, the diameter doesn't have any effect. No much effect on the diameter growth. Just you can see maybe more voids here compared to nanowire growth on the for 3 hours, okay, compared to 3 hours. Okay, that's all for synthesization process. So now we go for some of the application of ZnO nanowires. So there are actually many application for nanowires. Okay, as you can see here, field effect transistor, chemical and biological sensor, okay, UV sensor, what else? Several types of sensor, logic gates, nanogenerators, solar cells, okay, and also magnetic devices. So today I will show you a few, just two of application, which is the first one is the SSC solar cell, dye-synthesized solar cells. So current, as you know, who is familiar with the SSC? So the current or normal approaches to use, they are using mesoporous thin film or random nanoparticle network to produce the SSC from zinc oxide. But the problems are it will slow electron transport, and it is also difficult to fill electrolyte because there are lack of voids between the structure. So the use of aligned nanowires arrays will allow the enhancements of the absorption coefficient because of their largest area, direct pathway for electron transport, and also reducing the probability of electron-hole recombination. Okay, so hole can reach at the surface faster than other architectures. Architectures mean is the structure of the nanostructure itself. So this one is on nanowires, discussing on nanowires, and this will facilitate the filling of the pores with the electrolyte. Okay, here's some of the result. Okay, here is a position of zinc oxide by varying the time. So you can see that by varying the time, as shown before, when we are varying the time, the length of the nanowires will be increased. So you can see from the efficiency of the solar cell that has been fabricated. So the efficiency, this one you can compare. This one is without. This one is without nanowire. Just this one is the structure that we're using. So there is no wires here, just zinc oxide nanoparticle TiO2. So the efficiency is, we can achieve is 0.827%. Okay, but we can see when we applied the zinc oxide nanorod on top of the zinc oxide nanoparticles, so as we increase the time of deposition, the length of the nanowires increased, so the efficiency also was being increased. So we do not know, we do not test more than 60 minutes. So we do not know yet for now for how long or how far this efficiency can goes. But I think there is must be optimum length for this kind of structure, this fabrication of device. Okay, nanogenerators. Okay, this one is quite new for our groups also. Okay, so this is of the application of the nanowires. Okay, this nanogenerators is attracting substantial attention from all researchers because Zinc oxide is actually exhibit a highly efficient piezoelectric properties. So the function of nanogenerator is actually to convert mechanical energy to electricity. So as you can see here, this nanogenerator is actually, we can say that it can substitute the use of battery, because we just apply a mechanical energy for the device to convert it into electricity. So normally, a common that we know now, for example, for implantable devices for the use of patient who have a problem on uh, their heart. Okay, they are usually use a battery to support their lifetime of their heart. So by using, if they are using too long, then they have to go for next operation just to substitute the battery. Okay, so if the technology now can replace this kind of use of battery, so it might be a good research to proceed. So these electronic products are being miniaturized, okay, as you know. So in nanoscale device, the device of traditional rechargeable and replaceable battery are limited. So the development of this nano generator, to convert the available form of energy from environment into electric energy, facilitate the development of this kind of nano devices. Okay, nano generator can be used to develop batteryless system for future application, as I mentioned to you before. So in recent years, we can see that various articles have reported upon the piezoelectric properties of these zinc oxide nanowires, but most have focused on single zinc oxide nanowires, or nano. Some also have using nanorods, okay, instead of nanowires. Okay, this is some few investigation that have reported on zinc oxide nanowires arrays with glass, sapphire, silicon, and hard material to develop the nanogenerators. But this subset suffers from the difficult to enhance the piezoelectric due to the during the transferring the mechanical energy into electrical energy. The problem is it easy to crack after several times of uh, bending. Okay, bending on this structure. So in figure, you can see the compressive bending of the sample will increase its piezoelectric current, suggesting that bending increase the larger area of contact between the zinc oxide nanowires and this one. This one they are using zinc oxide nanowires. This one is zinc oxide coated with PT. So this device will be compressed with and applied forces. So compressive bending of the sample will increase the piezoelectric current, suggesting that this bending will increase the large area surface, okay, larger area of contact between the zinc oxide nanowires and the PT coated zinc oxide nanowires. Okay, so this is the result of the bending. Okay, so it was increased from 0 until 2.5%. So the current increases, we can see the current increases with the bending percentage indicate that the impedance decreases as the compression increases. So suggesting that the area of contact between the nanowire and PT nanowire increases with the compression as until the sample is deformed. Okay. So you can see here that after 2%, the current voltage is actually have some number of jump here. So this one is quite interesting. So be investigate more why this is happen. Okay. Okay, I think that's all. Just to introduce my lab members. Okay, so previously Dr. Asnida has already mentioned that I'm from Nanoscience lab. Okay, so here is our head of center, the Prof. Engineer Dr. Muhammad Rusok, and our researcher Dr. Zuraida, Dr. Asnida, our associate member Dr. Mary, Prof. Saifullah, our technical staff, our senior science officer, okay, TS Salifirus Muhammad Jaafar, and our senior research officer, TS Irmazatul Syedani, our assistant engineer, Mr. Azlan Jaafar, and also our assistant research officer, Encik Muhammad Faizal Abdul Halim. So with that, I also would invite anyone who are interested in our research. If anyone interested, no, actually I'm doing more on oxide materials. Dr. Asnida is more on carbon-based materials. Dr. Zuraida also doing on oxide materials and more on chemistry research. So you can anyone who are interested can come to us so we can collaborate, inshallah. With that, I will end my presentation. Thank you.
Okay, Alhamdulillah, very informative and interesting research. Okay, I believe many of us get some idea about this topic, how to synthesize the zinc oxide nanowire. Okay, Alhamdulillah. Okay, since they have no question in the chat room, so Dr. Firdaus, I have one question. What are the possible reasons to grow the zinc oxide vertical line as shown in your FSM image just now?
Actually, zinc oxide, as you know, it is a hexagonal crystal. So usually it is preferentially oriented along the 002 plane, which is the C axis. So when the zinc oxide is deposited on the substrate as a thin layer or seed layer, so it will act as a nucleation agent. So the shape, size, orientation of the nanorod or nanowire grown on the seed layer is depend on the grain size, thickness, and perfectness of the orientation of the seed layer crystal itself. So since the zinc oxide is a hexagonal crystal and is a preferential orientation along the 002 plane, so it will follow according to the layer that we have already synthesized before. Okay. Additionally, it also reported this 002 plane has a lower surface energy compared to the other planes. So the development of this nanowire can grow very easily along the C axis compared to the other axis.
Okay, thank you, Dr. Firdaus. Okay, we have two questions in the chat room. Okay, the question number one is, okay, thank you for very informative. Okay, I want to ask a question, how to produce stable collider dispersion of zinc oxide solution during synthesis process?
How to stable collider dispersion solution? For stable, I'm not sure if the one who asked this one is have a problem on the homogeneity of the solution or how. But in our research, we are using this sonication process to overcome or to overcome and speed up our zinc oxide formation? I need to know details. What does the person who asked this question, if more details information that he can give to me, maybe I can suggest. And then
Okay. Okay, the question number 2, Dr. Firdaus, which is better to optimize the potential of zinc oxide by modify the structure or by add other materials?
Okay, the first one is you want to optimize the potential zinc oxide for what? For what application? So you have to set the that one is in my opinion. So what actually you want to zinc oxide for solar cell and zinc oxide for sensor is different. So you have to know what you want to produce. So if you want to produce more on visible visible based electronic devices, so you have to you have to optimize towards that. So if you want to actually it is difficult to say because you have to set first what is your purpose. Okay.
Okay, so the next question,
uh, okay.
Dr. Firdaus, you can hear?
Yeah,
Hello? Yeah. Okay, the next question. Okay, what is your opinion of using nanowires as the cancer biosensor?
what is my opinion using
Yes, it's your opinion. When using a nanowire, use nanowire in the cancer biosensor application.
cancer biosensor? Okay, I'm not really quite familiar with this cancer biosensor. Okay, but actually as long as we have uh, as long as you can get the signal from how to get the signal using your material, so you can use for any kind of but it depends because I'm also not familiar on this cancer biosensor. It has some of it have to be justified lah.
Okay, thank you, Dr.
And
Firdaus. Okay, the next. Okay, can proceed the next question, Dr. Firdaus?
banyak soalan. Okay.
Okay.
Boleh baca sendiri ya. Would like to ask for solar cell application, does depletion region at each for solar cell application, does depletion region exist at each of the wire? Siapa tu? For solar cell application, does depletion region exist at each of the wire or rods? Depletion region mean the single rods or the single wire rods or layer of the usually the depletion region is between the what we call it, the layer of structure of the solar cell structure, not between the single wire or single rods. So okay, and then how to prove zinc oxide sample, for example, for how to prove that zinc oxide sample, for example, for photovoltaic application having a non-toxicity properties. Macam mana soalan ni? Tak faham. How to prove that zinc oxide sample? How to prove what? For example, Is it? Do you mean is it can be used in catalysis? Is it?
What I understand, how you prove that zinc oxide is a non-toxicity that can be used for the photocatalysis application. Maybe that is the meaning.
Normally, zinc oxide is it is non-toxicity and it is widely used in photocatalysis application. So, yeah, you can use, but I don't understand if the person who are asking have a different.
Okay. Okay, thank you, Dr. Firdaus. Okay. So there is no other question in the chat room. Okay, I have one more question, Dr. Firdaus. Why is zinc oxide considered as a choice for piezoelectric materials for nanogenerators?
Pardon.
Sorry. Why zinc oxide considered as a choice for piezoelectric materials for nanogenerators?
One of it that I know, the zinc oxide is being used or choose as a piezoelectric materials because due to their sufficient coupling coefficient compared to other materials like before they are using like what called the polymer like PVDF. Previously they are using that. So one of the reason is due to the sufficient coupling coefficient.
Okay, thank you, Dr. Firdaus. Okay, since they have no any question in the chat room, maybe you can end this session with welcome to audience to email you any question or what, Dr. Firdaus?
Oh yeah, sure. For those who want to ask me any question or anyone who already just asked from now, if you're not satisfied with your answer, you can email me using the UITM email mfmalik07@uitm.edu.my. So I will try to answer your question.
Okay, terima kasih. Thank you, Dr. Firdaus. Okay.
I will, but not for now after MCO.
Okay, Alhamdulillah, very informative and very interesting this research. Okay, so hopefully we can get some idea from this topic. Okay, thank you for the participating into this webinar. Okay, we hope to see you again next time. Okay, thank you.